right, picking up where we left off, parallel lines. So, two lines are parallel if they have the same slope. So that's the criteria for determining if lines are parallel. We'll talk about perpendicular lines as well, but let's keep on going. All right. So here's an example. Find a line that is parallel to a given line. So the key here, and I say this in different ways, but one way I like to say it is the goal we have is to make the slope visible. And when you're given an equation in standard form, that equation is not, the slope is not visible. The slope is not immediately obvious. So put it in the form y equals mx plus b. In other words, solve for y. And the slope will pop. The slope will appear. By the way, the slope is not minus 1/2 x. It's between the equal sign and the x. So the slope of this line is minus 1/2. That drifted a little bit on the upload. It looks like a few of the fractions did, but on this slide. But anyhow, slope is negative 1/2. Since the line containing the point 1, 0 also has a slope of 1/2, we use the point slope form. So I think we can see the equation underneath all of this. I don't know, it looks like there was an extra thing here. I got these slopes for these slides from the author's webpage, so you can find them there, hopefully with better format. But just substituting in here, substituting negative 1/2 for the slope, substituting 1 for x1 and 0 for y1, yeah, pretty quickly puts it in slope-intercept form. And this might be the first time they actually cleared fractions and gave an answer in the general form. I will say the general form is very popular, so don't forget that both forms exist, slope-intercept and the general form. All right, so two lines with the same slope. Take a little more time talking about perpendicular lines because there's a little bit more work involved here. So they tell you something true here. Lines are perpendicular if and only if the product of their slopes is negative 1. And that works really well for this situation. Negative 1 times 1 is negative 1. So if you have a slope of line of slope negative 1 and a line of slope 1, you know they're perpendicular. But remember, a lot of times we think of slope as the rise over run. We think of it as a fraction. And so I'll have another way of describing this in a second. Let's look at this example. So if you have a slope of negative 1/2, what's the, and you'll see me do this when two variables are related in some way, I'll call one of them prime and one of them m. I mean, it's not the same thing, it's different. But if m is your original slope, what's m prime if, in this one case, prime means perpendicular? You know, in other words, what's the related slope? All right, well, you can go with what they said and think mentally, negative 1/2 times m prime has to equal negative 1. Remember the formula, the two slopes multiplied equals negative 1. I wouldn't recommend that as a thought process because there's an easier one. So I just think of taking the reciprocal and changing the sign. Two-step process. Take the reciprocal of 1 over 2 is 2 over 1, and change the sign. If it was negative, make it positive. So it's going to be, once I simplify that, positive 2. I'll do another example. That was just almost too easy. Let's say I had 3/5 the perpendicular would be -5/3. All right. So we have a full example here. Find an equation of a line that contains the point -1, -2, and is perpendicular to this line. So right away we know we're going to solve for y. And if we solve for y, that will expose the slope of this line. So just take it down here, go through the process, and we know that m is between the equal sign and the x. It's -1/2. So that tells us the perpendicular line is going to have a slope of 2. And understand how important this is. I now know the slope is 2. I know my x1. I know my y1. So I can substitute everything into this equation here. Substitute, substitute, substitute. Our calculation continues down here. And I get the line in two different forms. I get the line in the slope-intercept form, and I get the line in the general form. So I know you have examples like this on the homework with a perpendicular line specifically. So definitely take a look at that. All right, last section is circles. And you really are going to need to know the standard form of the equation of a circle and everything that comes from that. So what is a circle? A circle is given to us with 3 measurements or 3 numbers. First of all, we want to know the center. Well, it's not really in order here, but we want the center. So there's H and K. Those are the values of the center. Usually we express that as an ordered pair. And R. R is the radius. And this is worth memorizing. This is the formula for a circle. Now keep in mind, H, K, and R are going to be numbers that are going to be revealed at some point in the problem, usually at the very beginning of the problem. But once you have those numbers, you should know exactly what graph you're talking about. Also notice the built-in minus. I think that's probably the most common error. The squares and the minuses are built in. So sometimes you have to adjust the numbers that you see to make this problem work. In other words, it's a really good formula for making H and K visible. R is kind of hidden because what you're seeing is R squared, not R, but it's an important formula. All right. Now they just go ahead and say, you know what? If H and K are 0, then the formula has this kind of special case. So another formula we should memorize. And they even talk about something called the unit circle. Not a big player in this class, but in some classes it's a big deal. Example 1, write the standard form of this equation. All right, so they're telling us it's a circle. So as soon as they tell us it's a circle, we say, all right, we need to find our H, our K, and our R. Well, R is 6, H is -2, and K is 5. Just from the information we have. So we're going to make those substitutions. And of course, when you substitute a negative number and there's a minus sign, those kind of get together and we have a +2. Plus is very important here. Y minus 5 squared and even 36. Now we're going to reverse this process, and that's mostly the way we're going to do it. So if we start here, your job is to identify what H is, identify what K is, and identify what R is from the equation. And that's happening next. All right. So here's a problem where they actually want you to graph this. Graph the equation x plus 1 squared, y plus minus 1 squared equals 9. You have to realize that this is a circle. Like step one is realize that this is x minus h squared, y minus k squared equals r squared. All right, if you realize that, you know we have a circle. And let me do this one here. R is not 9. R squared is 9. So that tells us R is 3. K, now this is a nice combination here. Usually when I'm comparing things on a formula, what I like to do is I just like to think of ignore everything that's the same. So ignore the parenthesis, the y, the minus sign, the other parenthesis, even the square, and just look at what's different, what lines up but's different. Well, that tells us right away that k is equal to 1. Now here, there are two things that are different. I have everything but plus 1 and minus h are different. Remember, the formula had a minus in it. So what that literally tells us is that if we cancel everything that's identical, what we're left with is minus h lines up with plus 1, which I don't want to know what minus h is. I want to know what h is. H is minus 1. So the author's going to get there, right? H is minus 1, K is 1, R is 3. That means I'm ready to graph this. And how does that work? Well, I first find the point, negative 1, 1, HK written as a ordered pair. And when I say ordered, H has to come first, K has to come second. Ordered pair. And then I'm going to travel 1, 2, 3 in every direction, at least north, south, east, and west in every direction, 3. So if I go 3, if I go 3 to the left, I go 3 down, I go 3 to the right, I have found these 3 points. Now, by the way, realistically on the computer, and I know you've already done this, I think everyone's already done it because it was question 1 or question 2. There's a built-in app for drawing circles. And what you have to do is you have to click the center and you have to click any one of these 4 points. But make sure you tug left, right, north, or south. I mean, you can't go sideways and get a good picture with that software on the computer. Anyhow, you click the circle icon, and the center and another point. And if you get it wrong, you can drag it later. But anyhow, drag the circle around by the center and 1 point, and the computer will do the rest. But if you're doing this by hand, it sometimes takes a little, steadiness and practice to go through 4 points with a good circle. But all right, that was graphing a circle. We were given given the equation. It didn't even say it was a circle. We were given an equation, we recognized the shape, and we used it. This is kind of an advanced idea that I really like it, though. If you did circles in Algebra 1 or Algebra 2, you probably did not talk about intercepts of circles, but intercepts are really kind of a helpful thing. And they let us use this idea that we should really know about for solving problems. So I'll introduce the idea. The idea is completing the square, or the square root property, actually. So the square root principle or square root property is if you have x squared equals, say, k. I shouldn't use k because that sounds like I'm part of a circle. X squared equals w. Then it's true that x equals plus or minus the square root of w. If you have any expression squared or any argument squared, I'll go with argument. If you have an argument squared equals w, the next thing you can write down is the argument not squared is equal to plus or minus the square root of w. And this is what I call squared side number side, and it's a really powerful thing to use. So if you have squared side number side, or you can get it, it's a good thing to find because you're very close to finishing the problem. So look at what they did. To find the x-intercept, we know we let y equal 0. We let y equal 0, and that made this -1 squared just a 1. And the author really worked for it. Squared side, number side. The author worked for argument squared equals w, where the argument is x plus 1. What happened? This is equal to plus or minus the square root of 8. Well, the square root of 8, he went ahead and simplified to 2 square root of 2, but it wouldn't have hurt to write square root of 8 for one step there. And then subtracted 1 from both sides. Here we are. We have the x-intercepts. And remember how the book works. If the letter X is in the name, the author's not going to write it as an ordered pair. The author's just going to write it as the numbers. So we have a little more information here. The intercepts are approximately -3.83 and +1.83. So what were those? Those were the x-intercepts. So those points right there. There's no way we would have just known what those were. We had to actually calculate them. All right, similarly, the author arranged squared side, number side for the y-intercepts. And so we have 4 intercepts, 2 x-intercepts, 2 y-intercepts for this particular circle. All right, now I did talk about completing the square first night, and the reason why I did that was I knew this moment was coming. So we have to be able to complete the square on something like this to make the problem work. What I mean by complete the square is I want x minus h squared. I don't just want it, I need it. I need to put it in its standard form. So this is called the general form, which is not what I want. I want the other one. I want the completed square form. So if nothing else, we could put the parentheses in here. Didn't really do much math, just took the x and the 6x, put them next to each other, put these next to each other, and took this 4, subtracted 4 from both sides, and I have this. I like to write it down this way, this step. All right, didn't really do any more math, but just kind of setting the table. I know that I'm going to put something here, and I know I'm going to put something there. And whatever I put here, I have to add to the other side of the equation. Whatever I put here, I have to add to the other side of the equation. So there's some method here. And we'll see it right here. The author added, and this should look familiar from just the little bit that we've talked about already. If I take this 6, cut it in half and square it, I get 9. That's why it's 9. If I add 9 on one side, I got to do it to the other. Take this 4, there's 4s all over the place, but take this 4, divide it by 2 and square it, I get 4. 4 is what I add there, and I'll add it here as well. And now, what perfect square trinomial am I talking about here? Well, it's x minus 3. And again, we could just figure that out by factoring y plus 2. We could figure that out. But it was a very quick process, but the process still has to be done. And you get the completed square form. We still have to interpret it. Notice that 9 is r squared, so r is 3. What am I subtracting from x? I'm subtracting a 3. What am I subtracting from y? Actually, I'm adding 2, so I can think of that as subtracting a -2. So it reveals its secrets by putting it in this form. So you've heard me say it, I call this making something visible, right? Making the invisible visible. So I usually put it this way. There's a type of question I don't really have a lot of patience for. And that is when somebody looks at the very, very beginning of a problem and says, how did you know R was going to be 9? Sorry, R wasn't 9, was it? It was 3. Yeah. How did you know R was going to be 3? I don't see a 3. Of course you don't see a 3. That's the whole point. You're not supposed to get to step 5 or whatever step it is before you do steps 1, 2, and 3 and whatever. So 4. So do the steps before you ask questions about the very end of the problem. So back to that. When someone says, how'd you know R was going to be 3? I would say, I didn't. Next question, right? You don't know in advance what it's going to be. That's why we had to do the work. That's why I'm not really a fan of that question, right? How did I know H was going to be 3? Didn't. How did I know K was going to be -2? I didn't. That's why we do the work. All right. So again, we do the process. Then we match everything up. And once I found out this was 9, I knew it was R squared. Hopefully you understand what I'm saying. I'm not saying I don't want to hear a question. I'm just saying that if you formulate a question, make sure it is not a question that just shows impatience and an unwillingness to do the process. All right. Well, they have, so then now they finally graphed that one. So if you remember everything, center, the radius, and gave you these points. I don't know if they're going to ask, yeah, it doesn't look like they're going to ask for the intercepts, but if I did want to find the intercepts, I could do that. Actually, notice there's just one intercept here at 0, -2. The way the graph touches and doesn't cross the y-axis tells me that, you know, the intercept is actually visible. This one would, I'm sure, have a square root in it if I did the work, but you'd have to actually do the work. All right. I'm not really a fan of this. We're not really going to use graphing utilities. Graphing utilities means a graphing calculator, which we don't use. But real quickly, what the author is saying is, if you do this and you get this, there's actually 2 different parts to this problem. There's the y equals the square root of 9 minus x squared, and there's y equals minus the square root of 9 minus x squared. And if you're going to use a computer to graph it, you would most likely have to graph both of them separately. You don't have to graph them in separate colors like they did here, but you know, they were just saying, well, graph one of them and graph the other, because a graphing utility like a TI-84 isn't going to let you put in a plus or minus. It's just one of those adjustments we sometimes have to make when you have a plus or minus. But graphing calculators are not required, and I really don't even talk about them other than to say I don't talk about them. But that's it. That's chapter 2 in a series of videos. I don't know if I addressed this, but not really sure if I'm going to do a chapter 1 or a chapter R on this series. That's a serious question. I know some students are have asked about that already. But I find doing review, you know, uploading videos for review becomes a slippery slope. Students seem to demand to be told everything that they were supposed to know. Like, am I going to review how to add and subtract fractions, how to, I don't know, plot points? Maybe. I mean, maybe I will, but and I if I get a chance, I don't mind talking about things specifically during the tutoring or the office hours that I have every week. But at some point, you do have to look up some things. Our website, it has plenty of help. I'm hearing this from students already. that, you know, they thought they had forgotten how to plot a point, and then it came right back to them by starting the homework, and that's exactly what I want to happen with the review. But if you're looking for Chapter 1 and Chapter R, right now, I'm going to do the more important, the more necessary chapters, the one where everybody needs an exposure to that. So what do I want you to do for Chapter 1? Well, use the resources on the website. There's no shortage of resources on the website. I think I might have mentioned this elsewhere. I found at least 6 hours of videos on Chapter R alone, and that was just under one page of my math lab. There'd be other videos in other formats. So there's plenty of information out there. But as far as this, that's the end of Chapter 2. All right. Talk to you in the next series of videos.